welcome everyone. Thanks for joining in on this webinar today. I'm going to be talking about this project that we did for the first year for the C2 Smart Center. I renamed the title a little bit. I'm calling it Integration of Artificial Intelligence in Mobility Services to Improve Seniors Accessibility. Mainly, this work is trying to develop a better algorithms to improve mobility service with a target audience of seniors, but looking at also more general applications. So as you can see on the title slide, I do include the team that was involved at the various stages of this project, including Asel, Dimitrieva, Gugu Yoon, and Danny Fei. So the project ended middle of last year, but we still have done a little bit more ongoing research on this topic, and the plan is to re-engage with our collaborator, University of Texas at El Paso, with Professor Kelvin Chiu, to look into this topic a little bit more for year 3. So we will probably update you more on that later in the year. Okay. At some point in these slides in the presentation, I'll probably pause a little bit and give you a chance to ask some questions, so that we don't have to reserve everything to the end. Okay. All right. So I wanted to start off by kind of pointing out, one of the key measures of planning, transportation planning, and that is really looking at accessibility. So this is one of the motivating factors. There's a lot of different measures of accessibility, and how do we, determine for a given transportation design, how does it impact, the opportunities available to people, to different groups of people, right? So here on this slide, you can see there's a bunch of different measures that have been developed over the years through the literature. I want to note that when you look at the elderly and senior citizens in particular, the accessibility opportunities can be vastly different, right? So in this graph here, on the upper side, you can see there's accessibility to healthcare facilities for the general population. And on the left-hand side, it's just the overall population. On the right-hand side is the overall population with car ownership, right, with vehicle access. And when you look at the elderly, this accessibility chart looks quite different. They have much more limited accessibility, and in general as well, elderly population has much less information available as well when they're trying to travel to access different employment or well, not employment, but looking at different services and opportunities to gain access to. All right. So how can we address this discrepancy in accessibility and mobility options for seniors? Right. This is a very important research need, because seniors currently make up a good percentage of trips. Right. As you can see here, they're about 1 out of 8 travelers are seniors with an age of 65 years or older, and they make up about 10% of all miles traveled, according to AARP a few years ago. And this is only going to increase in percentage over the years, because our population is aging. Right? This is a graph from the UN World Population Prospect in 2008. And because of this, we can also see that the share of senior transit users, particularly, right, just so looking at transit mode access, seniors have increased the market share by 40% from 2001 to 2009, which is more than 1 billion trips over that time period. So you can see that it is quite an important need that needs to be addressed. When we look at the kind of solutions and tools to try to provide, answers and address those kind of needs to better serve seniors, we find that it's a bit lacking. From a survey conducted by Forbes in 2015, they found like the top 6 smartphone apps for seniors. You can see them on that list, and there really aren't that many solutions related to mobility for seniors. And so the question arises, whether seniors need, whether having more of these kind of mobility solutions from using mobile apps and better technologies can really improve access for seniors or not, and how we can implement them, right? Okay, so let me go by first describing the first part of our project in the year 1 C2 Smart project that we conducted. And this was in collaboration with Professor Chu at University of Texas, El Paso. Basically, we wanted to better understand senior mobility needs. Okay, so we conducted a series of surveys, both in El Paso and in New York City. On this slide, we summarize the efforts from the UTEP team, where they conducted surveys with different senior centers in El Paso, 11 of them, through November 6th to December 1st in 2017. They had 17 questions on this survey questionnaire that covered topics involving demographics, lifestyle, mobility needs, smartphone apps. And they also drafted in English and Spanish. They had about 460 responses, 73% of which were senior citizens. Right. Based on this survey, they found that, and of course this makes a lot of sense, right? A majority of the respondents did not own smartphones. 10% expressed interest in an app of educational courses were offered to teach better use of those apps, and 78% were willing to anonymously share the data via the app. Okay, how does this compare with New York City? Okay, now we also took a look from New York City. We conducted a survey that Acel helped conduct. So this was from February 5th to February 16th in 2018. We surveyed 5 senior centers. The number is less. The number of respondents was less than at the UTEP. We intended this survey to be more of a supplemental survey to add to their survey questionnaire, so that they can get a broader set of responses. We had 61 respondents, 77% of which were senior, this was a little bit similar to what the El Paso team had. In our case, we had about 60% African American, 75% of them spoke English with confidence, and the zip codes for these locations were largely in the Upper East Side, East Harlem, and there was one location in the Washington Heights area. Okay. So based on those survey results, we found that 51% of our respondents reported having no disability, or rather, looking at it the other way, 49% of them had some form of disability. Among those with disability, 36% involved walking disabilities, 15% with visual, and 10% with muscle control. So those were the most common ones. We also found that 62% of them used a smartphone, which actually is quite a significant number. And 70% of those respondents that we found did not need assistance with the devices. So it was a more encouraging finding in the New York City case, and we think that this is given the setting within a larger urban area that it had this type of finding. 80% of these users never used Paratransit. Only 13% of them used ride-sharing service. That was something of interest to us because we particularly wanted to look at the opportunity of providing smarter mobility services to these seniors. One of the motivating factors for using apps for mobility was better navigation. So that also makes sense. For us to provide solutions to elderly, we want to be able to target their specific needs, and navigation seems to be one of the main uses. And that use of navigation is primarily to tackle concerns related to travel time costs or extreme weather, basically a lot of uncertainties that seniors might encounter when they travel that they want to counteract with a better navigation use, right? So based on those initial survey results, it led us to thinking about ways to addressing these challenges in senior mobility, okay? And so we took a look at the studies that have been conducted on paratransit service, right? Paratransit, like Access-a-Ride, is a required service that's provided to people who have need of it. You can take an Access-a-Ride service if you qualify for it for the same price as any transit ride in the city. This provides access to a good number of the population. As you can see from this article, about 144,000 elderly and disabled people are able to make use of Access-a-Ride for travel per year, which equates to about 400 seniors per day, which is quite a sizable number, right? So the flip side of this is that it's very costly. So while these seniors might be paying only nominal fees to make these trips using paratransit, it's costing the paratransit and the MTA about $461 million per year, as according to in 2015, and this averages to about $71 per trip, right? Which is quite high. So how do we dissect this cost? Okay, so if we take a look at the trips made by paratransit, one of the key challenges in maintaining the costs is the fact that they're dealing with schedule changes that are unanticipated. Right? One of the most common ways that a paratransit schedule might be disrupted is if passengers have no-shows or they cancel very late in the game. That causes the service to have to reschedule the service to accommodate. Okay. In addition to that, schedule changes can also be caused by travelers having incidents that might arise due to other related services. So some travelers might be using Access-a-Ride or just general mobility services as part of a trip chain where they might visit some location and then maybe make a trip later on via another alternative, let's say MTA. And if they have need of elevators or escalators, for example, this can be a problem because they find from the MTA that an audit that was conducted, they found that a large percentage of these escalators and elevators do not receive their scheduled preventive maintenance assignments, and it results in a large number of these elevators being failing and down much of the time. So that's an issue that can also impact these kind of mobility services to provide service to travelers, particularly elderly, who have less information available to them. Okay, so what can we do about that as a center focusing on smarter transportation research? Our hypothesis here was that we can try to develop smarter, essentially autonomous mobility on demand services to respond to these schedule changes. Right, so on this graphic on the left-hand side, you see that this is a general mobility on demand shuttle service where I'm moving my mouse around. Alyssa, can you see the mouse?
Yes, I can see it.
Okay, great. So this mobility on demand shuttle is picking up a passenger here and dropping off that passenger at this location. And along the way, this shuttle has already been assigned 2 other passenger waypoints. And that's the standard way of operating a lot of these mobility shuttles. They're operating in real time. Passengers come in real time, and they're being picked up and dropped off on demand to these various locations. But if there's a disruption such that this destination might not be as feasible anymore, what can this mobility shuttle do about it? Right. So an alternative is we can recommend alternative destinations. So in this right-hand figure, you see that this same shuttle might now recommend 2 alternative destinations, destination 1 in red and a destination 2 in yellow, where basically they might be able to serve the passengers' destination needs in similar ways that they might be willing to take those alternative destinations instead. Right, there might be many occasions where this makes sense. For example, if the passenger is going shopping or going to eat at a restaurant, or looking at different, like visiting like a recreational area and so forth. And perhaps if we're focusing on, let's say, like medical appointment, that might not make as much sense because then that's probably requiring rescheduling. But here we're looking at the opportunity to provide alternative destinations so that the cost that the mobility shuttle has to endure can be mitigated. Right. So if we take a look here at this same figure, the destination 1, if it's to be embedded into the route that the mobility shuttle takes, you can see that if you just imagine the sum of the lengths of these links. That length is much shorter than what you would find if it was looking at the yellow links added up together, right? So in this sense, even though a passenger might be indifferent between just purely based on the destination 1 and 2 on their location, on their on the services provided by those 2 destinations, it can save in costs. And these costs can be reflected in terms of savings, which can be to the mobility shuttle in terms of fare prices, or in the case of Paratransit, it could result in reduced costs so that they can improve their service levels in other areas, and they can reallocate the budgets. Right. So thinking about these autonomous mobility on demand, AMOD types of services, if they're able to recommend destinations, what can they do? We can see that with this capability, recommending alternative options, for one thing, it can mitigate costs that arise due to unplanned disruptions or schedule cancellations. It can suggest new destinations entirely, where perhaps if the user, the passenger, has limited access to information in the first place, that this might be able to supplement that, right? So this recommender service can provide information to users who have not explored establishments beyond their typical neighborhoods, right? So elderly can be a particular target audience for this. And this type of capability allows the users to also, you can learn about, the system can learn about the user's responses about different destinations. So that can be very useful for efficiently learning about users' preferences so that you can provide the right type of service to the population. So given all these benefits, why don't we see this feature more present in the current MOD systems? Okay, so when we dig into this a little bit more and try to understand the underlying mechanics of destination recommendation, we see that there are certain unique challenges. Right. So to start off, let me describe what we mean by recommender systems. So when we recommender systems, we are looking at services that are using algorithms to better learn from and to serve customers. One popular type of algorithm is called a contextual bandit algorithm. And you can see a lot of examples of this online these days, right? So Amazon recommends similar items to you. Netflix as well, they can recommend similar items to you based on your preferences over time. And the more and more you use it, the better they're able to make recommendations suited to your preferences. Even Google with their targeted ads, for example, when you search for something, they will also recommend targeted ads at you. So this can be useful. I mean, targeting ads itself can be a nuisance, I guess, in many cases. But at least for mobility service, it can be quite useful as a tool to provide recommendations for destinations to users. Right. So that's what we're thinking, what we have in mind. And so how does this work? How do we recommend destination preferences on an AMOD service? We have to keep in mind that the way that the way this operation is happens is we can think of it as a series of trials, right? So there's a T number of trials that occurs over time. At any particular time where small t, the system has to make a recommendation of up to J different alternatives to recommend to a user, with the hope that when they make that recommendation, over time, the measurement of how successful the recommendations are is based on the cumulative rewards that the users and the system have attained at the final time period, at the final length of the number of trials, right? And you can compare different alternative algorithms, right? So one recommender service system might look like this blue trajectory, where initially at time t, this little t, it seems like in terms of regret, right, which is a measure of how far off they are from the best choice that they have available, that they've understood up to now, right? And the higher the regret, basically in terms of in an uncertain environment, the worse off this algorithm is, because it's not able to really learn their properties over time and provide a better solution, right? So that's the layman explanation of this, right? So in this case, it might seem like the blue line has poorer average regret up to time t, because so far it's higher, but that might be because this algorithm is doing some more exploration early on of different alternatives and learning from those experiences, so that afterwards it can improve upon the service and reduce the average regret significantly, right? So we want to be able to understand, how well these kind of algorithms can work in different settings, because one can potentially work very well in a certain setting, but be worse off in other cases, right? So far we've talked about recommender systems in general. The way that they operate in mobility service is that now you have additional route constraints, meaning when you're providing the recommender system, when the recommender system is providing a recommendation to the user, what that really means is it's selecting a destination for that user, for which the service, the shuttle service, would then have to transport the user to that location. So here, the operating costs and the passenger travel costs can vary significantly from trial to trial. Right? That's one of the unique issues here, because if you think about only the ratings of different destinations, like let's say if we look at restaurants, the quality of the restaurant, if we assume that, let's say like Yelp ratings, for example, can qualify for evaluating the quality of different restaurants in the city, you might see that one restaurant has a 4.5 versus another restaurant which has a 3.5, and you would assume that people would generally prefer the 4.5 more. But if in one trial a person is located much farther from the 4.5 than the 3.5, then that can impact their decision to prefer the closer location instead, right? So, and this changes trial by trial, because each passenger case where you have to make this recommendation can be a completely different scenario. So as an example, we have an establishment on the Upper East Side of Manhattan. Maybe they have an average rating of 4.5 out of 5. And because the user's initial location and the price of transporting the user to that location can depend on where they're starting off, that will impact the final recommendation. And these costs, right, in terms of the price of transport, are dependent on a number of different factors that are determined from routing optimization, right? These can depend on, for example, how many current passengers the shuttle is currently assigned to serve, what their demand patterns are, like where their origin and destinations are, what is the vehicle capacity, and so forth. Right. So, these highly contextual parameters can impact the recommendation. But so far, we don't really have a clear idea of how they impact these recommendations. And if you think about having a solution for one city, having a carefully tuned and designed recommender system for one city might only be useful for just that one city, because as you can see from this slide, even the patterns of demand can be significantly different from city to city. Right? This is showing the heat maps of establishments from Yelp Open Data in Las Vegas on the left and Toronto on the right, and you can see that they vary quite significantly in terms of the centrality of the patterns, the densities, and the way that they're dispersed. Okay, so it's important that we better understand these trade-offs so that it helps in extrapolating and tuning these algorithms in the future for deployment in different cities. Okay, and that leads us to the research question, right? Ultimately, our objective here is not to necessarily just to design a recommender system algorithm. What we really want to know here is what is the sensitivity of a destination recommender system to different routing settings. Okay. So to support that research question, to try to answer that question, we designed this algorithm based on there's a very common one called upper confidence bound algorithm, where within each trial, essentially a new customer would arrive at a pickup location. They would initiate this recommender system to suggest a destination. So imagine if it was like an Uber service that maybe many of you might be familiar with. If you were logging onto the Uber app, instead of selecting your final destination, you just say you want to go to a restaurant. And the Uber app would now recommend one or more restaurants to you to select from, right? So here the destination selection is based on a mix of optimizing the current level of service for the user, but also seeking to better learn from this experience so that they can better serve this and other users in the future trials. So the optimization becomes this combination of destination preference via Yelp ratings, for example, and as well as in terms of increasing route costs, right? So you want to pick a location that might not significantly increase route costs, so that reflects ultimately a lower fare price for the user. And the routing costs can be decided by an insertion heuristic for a traveling salesman problem with pickups and drop-offs. An example of that can be illustrated here. Here we see a grid, a 10 by 10 grid, where you have a vehicle located right here, this white triangle. It's currently carrying one passenger already. There's one passenger on board. This passenger wants to go to this location, and there's two other passengers that want to be served. located at this location and at this location, and they want to be dropped off at these two other locations. All right, so the insertion heuristic basically sequentially adds each location into a sequence of location visits, such that it minimizes the some objective. In our case, it's trying to minimize the operating costs of the transport costs of the whole sequence of visits. And it also makes sure that in our case, the visits do not violate precedence conditions, meaning you cannot visit a passenger's drop-off location before you visit their pickup location, right? So that has to make sense. So one example of a solution based on this insertion heuristic would be this one, where this vehicle would now go pick up this passenger, then this one, then drop off, and finally drop off. In this case, the vehicle's capacity is at least 3, as you can tell from this. Okay, so now we take this algorithm, this insertion heuristic, and we embed it into the recommender system, or at least a contextual bandit learning algorithm. And what this looks like in a Manhattan setting, you can see let's say there's a initial vehicle location, and this illustrates what it could look like in a single trial prior to a new passenger coming on board that requires recommendation. Okay, so this might look like a case where, let's say, this vehicle has 6 passengers that they need to serve. The circles represent the pickup locations, and the squares represent the destination, that's drop-off locations. So, for example, this location is the pickup for passenger 1, and this is the location for drop-off of passenger 1. And based on considering all possible connections between nodes, the insertion heuristic would find a sequence that would satisfy the precedence constraints while still dropping off everyone, and also ensuring that the vehicle capacity is not exceeded. Right. So fairly straightforward approach to considering how to assign passengers to this vehicle in what sequence. So based on this existing condition, now we consider a new passenger where there's a given route already. So this vehicle has already been assigned to a couple of passengers along the way. It's en route when suddenly passenger 6 comes online, located at this location, and they request service with destination recommendation. So what happens then? The recommender service now would pull up a database of different destination locations. This could be a pool of different restaurants, and based on that pool of restaurants, it would recommend. The recommender service would choose one of those locations. In this case, it happens that it turns out to be location 98 because it optimizes the algorithm, the objective of the recommendation algorithm, and it would now select location 6 to incorporate into its sequence. So now it would have a new rebuilt route that adds location 6 into its location 6 or pickup, as well as the recommended destination into the sequence of visits. Okay. And so that gives us an algorithm for the recommender system. So I'm about to go into like some of the experiments, but before I do, I can pause here. Are there any questions from the audience, from anyone? If not, I can keep going first. Okay, I think I'll just keep going then. So that illustration in the previous slide shows us how the destination recommender system happens within each trial. We first wanted to see, okay, given that that's how it's working, we want to verify that if we run this recommender service over multiple trials, it does succeed in learning the preferences of users firstly, and that's the objective of the first simulation experiment that we conduct. This is a system verification experiment, and then a second experiment will be conducted with more realistic data to better understand the elasticities of different routing parameters. Okay, so in this first simulation experiment, the system considers a scenario with 100 destinations, so they're uniformly distributed across a 10 by 10 grid. You have a single shuttle running along this grid region, and there are a number of trials. In our case, I believe we pull up to 1,000 trials. Within each trial, a randomly constructed scenario is created. So within the scenario in each trial, there's a randomly drawn number of existing passengers assigned to the shuttle, plus a newly assigned passenger with a need for a destination recommendation. Right, so the recommender system would now have to look at each of the 100 destinations and recommend a location to that passenger so that it can provide good service to that passenger and also learn about the preferences over time. In this case, we have two parameters that we're trying to better learn. One is how the customers' ratings for these locations, the average ratings from the population, impact the user's preference for taking for a location, and the additional routing costs that the passenger adds to the route, how that impacts their preference for taking this service. Okay, we will assume that their behavior strictly follows a random utility model based on those two parameters that we predefine, but then keep hidden in this experiment. And then we want to see if we can run the set of trials so that it can review those hidden parameters. Okay. And taking a look at that, the setup of the simulation looks something like this. We have 100 different locations. Each of the locations has a predefined simulated, let's say, a Yelp rating, right, out of 5. For this case, we only look at locations with ratings between 3 to 5. And so, for example, this location right here at 2.2 has a very high rating. So it's about like, I think it was like 4.9 something, okay? Whereas this location over here is probably closer to a low 3 point something, right? And so the utility function that we're assuming here, and we tested out different values of this. This is not estimated from real data. We just constructed this utility function such that, for example, a destination with a rating of 4 and a route cost increase of 15 minutes would have an 81.8% acceptance rate, whereas if the rating drops to 3, the acceptance rate drops to 37.8%. So that felt like it's somewhat realistic, and we decided to use this set of parameters to see if the revealed rating values can be replicated. All right. So we run this experiment up to 1,000 trials. We start off with a 12 trial learning period to get some initial samples to start with. And this is what we see. We get a cumulative regret that kind of plateaus off because, as you can see, the average regret over time starts to reach a minimum amount after a while. And what we end up with in terms of estimations are these parameters for the intercept as well as for the rating and the routing cost increase, and they're pretty similar to the actual values, the hidden values, and you can see how they pretty much converge towards the values even by 300 iterations, right? So that's great. So within this fictional setting, it seems to work fairly well. How well does it work in, well, before we get to how well it works in a more real data setting, we also wanted to look at, what this means in terms of balancing the recommender system between exploration and exploitation, right? So exploration refers to the need to look at more other outcomes, other alternatives that might not be necessarily the best solution at the current stage, but they can inform the system so that it can make better recommendations in the future. Right? Exploitation is to kind of ignore that exploration, but to just try to provide the best service now, right? And that's really the trade-off. And if you think about it in a 1,000 trial series, you would tend to try to have more learning in the beginning and more exploitation in the end, right? So in this case, what we saw was based on the recommendations, some of the locations that had the best ratings ended up being recommended the most, and it was you can kind of see that the ones particularly that were more centralized tended to be recommended more. For example, 73 and 77. I think that just in terms of the patterns of the travel, they tended to occur. They tended to be recommended more often as a combination. So you can see that this combines the weights a little bit, right? So here, when we show how these ratings spread out, ultimately, out of 1,000 trials, this service does recommend a number of different locations, right? So there's a couple over here, there's a couple over here, but they will end up recommending a couple of key locations that have the best ratings more frequently than others, right? So that seems fairly well balanced, and that's good. And in fact, in summary, if we take a look at the acceptance rate, the algorithm can recommend appropriate alternatives to users to reduce regret of choosing alternatives with lower benefits, and it was able to estimate coefficients of the choice model that were fairly close to the real values. In this test, we saw that 42 zones out of the 100 were not recommended at all during simulation, and that's partly based on the construct of the true choice model, as well as the selection of the weight for exploration. And based on that combination, we saw that the average acceptance rate was about 52%. Right? And this can vary, so it can vary based on circumstance of the choice model and the setting of the trials. And in fact, if we take a look at the experiment 2, we end up with a vastly different acceptance rate. So in this experiment 2, we applied this to real data, at least as far as looking at real establishment locations with real Yelp ratings. The choice model that we have for destinations is still based on the same assumed model. The drawback of that is that in terms of magnitude of the acceptance rates and so forth, those wouldn't really make sense. But as far as comparing elasticities of the outcome model in terms of how sensitive the acceptance rate is to various routing constraints, that it's adequate to make that kind of assumption. So we consider a scenario in Manhattan with a single shuttle again. Now the passengers' locations are scattered throughout this region. Their densities are based. Yes. You have a question?
等会儿啊，你再说一遍。
Okay.
再刚我们去掉一个。我首先我有个 feature ranking， 去掉 ranking 掉第一个那个。
Excuse me?
那个是吧？
Can you repeat that? I can't.
Hi, Joe. I'm not sure if you can hear his question,
Yeah.
but he's asking, is there a way to take into consideration the cost of the return trips? And then he also asked, in your simulations, it seems the algorithm uses 1,000 trials to learn. In the real world, does that mean you need a lot of responses from each individual to learn?
Yeah. Yeah. Okay. So yeah, very good questions. The first question about well, let me answer the second question first. In terms of number of trials, we ran up to 1,000, but we found the way that we constructed our choice model right now is very small dimensional. It's just 2 parameters. So it actually learns quite quickly. And in fact, based on the way that we designed it, it learns very, very quickly. In reality, we're right now testing having alternative specific constants that have to be estimated within each of the locations to see how that would impact the learning rate. But yeah, it's quite efficient right now. As far as the first question, can you repeat that again, Alyssa?
Yep. The other question is there a way to take into consideration the cost of their return trips?
Oh yeah. So that's just modifying the routing function so that you add in the return trip into there. Since we were looking at this as more of vehicles operating on demand, we didn't specify a return trip, but you can certainly add that in. Yeah. Okay. So let me continue with this. So basically, we consider a scenario where a single shuttle, 1,000 points are generated, and then the restaurants are taken from a Yelp data set. With the ratings for the Yelp data set are very discretized to every half point. So it's like 4.5, 4, 5, 3.5, so forth. For each simulation run, we would randomly select 100 of them from this pool to make recommendations for. And what our research goal here for this experiment is to make multiple runs. So we actually run 200 different runs with different randomly generated routing constraint settings and randomly selected establishment locations so that we can evaluate the elasticity of the acceptance rate to these attributes. And you can see a little bit more about this here. Basically, as you can see, the utility functions staying the same for now, although we are testing making this a variable as well to have to learn in the future. And we are looking at basically the same assumptions of like the number of trials, but the parameters that we are modifying in each case, we're considering different vehicle capacities, integers between 4 to 8. We're considering different passenger arrival rates. So like higher arrival rates mean that for a given new passenger trial, they might have many more passengers on board or assigned to the shuttle during that time, during that trial. So that impacts the routes constructed when comparing route increases. And then the travel time conversion factor is representative of like the congestion level, right? So the higher the number, that means this is minutes per kilometer, so it's kind of like the inverse of the speed. So the higher it is, the more time it takes to get to the same, to travel the same distance. So the lower the value then refers to a faster operating speed. And then the exploration factor refers to the exploration parameter in the contextual bandit algorithm. And you can see this is what we're doing. We're running about 200 simulation runs. Each one goes up to 1,000 trials to see how the acceptance rate compares. And in terms of results, we see that the learned parameters result in pretty similar numbers. And across the 200 simulation runs, we get about a 90% average acceptance rate with a standard deviation of about 4%, 4 percentage points. So this seems to be pretty effective. But again, I think partly it's because right now we're assuming the alternative specific constants are given and known beforehand. Or not that they necessarily known, but that they're the same for every alternative. So it's a constant that's uniform across all the destinations. But I think if it's different per each destination, it could be a much more interesting result. And then lastly, we look at how the relationship between the acceptance rate and the parameters look for across those 200 simulations. So we take those results from the 200 simulations, we model it with a linear regression, and we see that based on this regression model, we can compute elasticities for the statistically significant parameters. Turns out the vehicle capacity was not that significant in determining the acceptance rate, but out of the other three, the exploration factor does impact it, as well as the passenger arrival rate and the travel time per distance. And among those three, the travel time per distance seems to be most impactful, meaning if you want to have an effective learning algorithm in a particular city, it seems like picking cities with lower congestion is more important than the other two factors that we've looked at. So that's something to consider. And these results are fairly recent, so we're still playing with them a little bit more to see what else we can learn from this. All right. So to wrap up, so far we've been incorporating these contextual bandit algorithms, which are a type of artificial intelligence into destination recommendation for these automated mobility on demand services, so that we can more efficiently make locations more accessible to elderly as one target audience, but also to other potential applications as well. We do have a prototype that we host on our GitHub site from the Build Lab. And we've presented this work at a couple of workshops. There was an NSF workshop last year, and there was a meetup at Sidewalk Labs. We presented this at UC Santa Barbara at the IATBR, and there was a presentation given at the Smart Cities conference from IEEE. The next steps right now, as I kind of alluded to in the beginning of the presentation, we are looking to do another collaborative project with UT El Paso with Professor Kelvin Chu. One thing we're interested in is taking their urban connector app and perhaps incorporating this destination recommender system into it so that we can test it. This would probably also require us having to actually build in more of this singular value decomposition component to really exploit the latent classes within the alternatives that exist between the different users. And lastly, we are also looking into considering using this contextual bandit learning algorithm in other mobility contexts, such as having better, more adaptive route design and network design algorithms. Okay, and that pretty much sums up my presentation. These are some of the references and the acknowledgements. This is, as I mentioned, it's a project from C2 Smart. This is one of the year one projects. We did have some help from various agencies in El Paso and in New York City to help us conduct those surveys. And we have a final report, a conference paper, and we're working on a final journal article right now that we're getting ready to submit for publication. Okay, I'll open up to any more questions that the audience might have. Thank you.
All right, it looks like that's it. I haven't seen any further questions, so thank you so much, Joe, for presenting today.
You're very welcome. Okay, so should I just click stop sharing and hand it back to you?
Yep, go ahead. All right, thank you to everyone for attending.